Welcome to Spring LIB.
For this problem on the topic of electromagnetic induction, we are told that the magnetic field within a long straight solenoid with a radius r is increasing at a rate of dB dt. We want to then calculate various properties of this magnetic field. We firstly want to calculate, in part A, the rate of change of flux through a circle with radius r1 within the solenoid. Now we know that the rate of change of magnetic flux d phi b dt is equal to the area, the cross-sectional area A, times the rate of change of the magnetic field dB dt, since phi is simply b times A, with the cross-sectional area A being constant. Now we know this is a circular cross-sectional area, so this is pi r1 squared, where r1 is the radius, and this is multiplied by dB dt. So here we have an expression for the rate of change of magnetic flux through a circular cross-section of the solenoid. Now in part B, we want to calculate the magnitude of the induced electric field inside the solenoid at the same distance r1 from the axis. We then want to show the direction of this field in a diagram. So firstly, to calculate the magnitude of this field, we know the electric field E is equal to 1 over 2 pi r, or 2 pi r1 in this case, times the rate of change of flux, d phi dt, magnetic flux. And so we can write this as pi r1 squared over 2 pi r1. Our expression for d phi dt comes from our first answer, and this is multiplied by dB dt, the rate of change of magnetic field. And so this becomes r1 over 2 dB dt, and that's the magnitude of the electric field. And now we need to show the direction. So here we have a diagram that shows the direction of the current, the magnetic field, and hence also the direction of the electric field. So we have the magnitude and direction of the induced electric field. Now in part C, we are asked to find the magnitude of the induced electric field outside the solenoid at a distance r2 from the axis. So all the flux we know is within a distance that is less than the radius of the solenoid. So outside the solenoid, we have E is equal to 1 over 2 pi r2 d phi dt, and this is equal to pi r squared, the radius of the solenoid, over 2 pi r2 dB dt. So there's no flux emanating from any point outside the solenoid. And so simplifying, this gives us capital R squared over 2 r2 times dB dt. And there's the magnitude of the induced field outside the solenoid. Now, in part D, we are asked to draw a graph of the magnitude of the induced electric field as a function of the distance r from the axis, from the points r is equal to 0 to r is equal to 2 times capital R. So as we can see, the electric field increases linearly with distance to a maximum at the radius of the solenoid, capital R, and then decreases exponentially as the distance increases away from the solenoid. The next question is E. which asks us to find the magnitude of the induced EMF in a circular turn with a given radius of r/2. So at r is equal to half the radius, the induced EMF epsilon is equal to d phi dt, the rate of change of the magnetic flux. So this becomes pi r/2 all squared. Remember, we have an expression for d phi dt, and this is times dB dt, the rate of change of magnetic field. So this simplifies to pi r squared over 4 times dB dt, and that's the EMF at the given distance. Now for part F, we want to calculate the induced EMF at a different point if the radius is now the radius of the solenoid r. So at r equal to the radius of the solenoid capital R, the induced EMF epsilon again is d phi dt, which is now pi r squared dB dt, and that's in the simplest form, so that's the EMF induced at the radius of the solenoid. Now finally, for question G, we want to know the induced EMF if the radius is now 2r. So we'll follow the same procedure. At r is equal to twice the radius, 2r, we have the induced EMF epsilon, again the rate of change of magnetic flux d phi b dt, which becomes pi times 2r all squared dB dt. But since there is no flux, this is actually pi times r squared d phi dt. So no flux can exist outside the radius. So the maximum radius has to be r squared, and hence the induced EMF exists only at the surface of the solenoid, and it's again pi r squared dB dt.